Hello everyone, I am Pavlo Dral, a professor at Chemen University and the main designer and developer of MLatom, the package for AI-enhanced computational chemistry. Last September we released version 3 of the package with tons of improvements. Since then we summarized its capabilities in the form of an academic paper, which got recently published in the Journal of Chemical Theory and Computation. And you can download this paper for free as it is open access. And even better, we adapted the material in this paper into a more interactive tutorial available online on the MLatom documentation page. And you can see the link to this documentation page in the description to the video. The advantage of the online tutorial is that we can directly show examples of how to use the package. And of course, in contrast to the static paper version, we will update it regularly. For example, when you go to the overview page of MLatom's documentation, you can directly click on the topic of interest, which would lead to the tutorial. If you want to check how to do geometry optimizations, you can click on the relevant section and just jump to the tutorial, then see how it works by yourself. And before I talk about some specifics, let me first describe what is MLatom. And MLatom basically leverages the power of machine learning to enhance typical computational chemistry simulations via user-friendly input files, and at the same time allows the user to create complex workflows with Python. And when we dive into MLatom capabilities, we see that it enables simulations with diverse quantum mechanical and also machine learning methods and their combinations. And these simulations include what you would expect from typical computational chemistry software. So it allows you to do optimizations of geometries, frequency calculations, simulate different types of spectra, run molecular dynamics, and it also enables you some unique techniques like two-photon absorption spectra with machine learning. So the package actually caters to both users and developers. That's why it can be used by users by simply providing input file and running the job, or you can do it via command line, or you can also design your own workflows using it in Python. And to show you an example, this is side-by-side comparison of how you can use MLatom through command line input file and Python API to do geometry optimizations. The input is quite intuitive, so you need to specify the task which you want to do, which is geometry optimization, and then choose the method. There are different types of models which you can find online which are supported. So it's from DFT to coupled cluster and semi-empirical methods and different your own trained machine learning models. And then you need to provide initial guess for geometry in XYZ format, and at the end of calculation you will get optimized file. Again, advantage of online tutorials that you can actually check how to do this for yourself. So first of all, you can download the package from the GitHub. You can install it via pip install, and even better, you can run it on the cloud computing without any installation, and that's for free for academic users. And I will show you some examples. So if we go to the very first one, here is a initial geometry which you can copy paste, or you can download the file. And once you download it, the file, you also need input file. Here it is, so you can again copy it or download it, and then we can go to the cloud computing. And here if you go to the job submitter, you provide your the job name, for example, as ethane optimization. So we try to optimize now ethane molecule, and then we put here our input, copy paste input file, or you can upload it. And then you need auxiliary file, which is basically in our case, initial guess for geometry. So we uploaded this file, confirm it now, and the only thing we need to push is now submit button, and the job is already running, so you can check in the job manager what's going on. So the job is running, and we can check output while it is running, and you can already see that it just terminated. So it was really very fast, 3 seconds, because we use machine learning approach, and this approach is even more accurate than DFT, like this relief for this molecule, and it's much faster, as you saw. In the output file, you can also find useful citations which you can put into your paper, and then you can check more what is in your output directory. So this is output file which we just saw, where you can check again convergence of your optimization, final energy, standard deviation of neural networks, because it has 8 neural networks. And then you can check your optimized geometry, which looks like this. And then you can double check that it should be the same as in the paper, so which is here. And more than this, so you can also run the same simulations using Python script. And here's an example. So it's pretty straightforward too. I will not explain all the details, but basically you first need to import MLatom as a Python package, and then you define the model, which is Ani1CCX. You create your molecule object, and then you do geometry optimization with this model, starting from initial geometry. And at the end, it will print you out final XYZ coordinates and write the file with optimized geometry. So we can do it in the terminal. When we go to our simulations, which would be basically the same initial guess, and that's why we can create our Python script. Let's call it like this, copy paste it, save it, and now we can run it as a normal Python executable. So it is pretty fast. Again, it provides you exactly the same geometry as with command line option or input file, and you can directly see for small molecules the progress. So it's a very nice way to develop even more complex workflows. Now when we go back to the tutorial, it provides the same way as in the paper, description how it handles data, because MLatom is a data-oriented package. So we saw already that, for example, internally it creates molecule objects, which consists of atom objects, and then you can have molecular databases for which you train your machine learning models. And then you can also have some special objects like molecular trajectories, which you dump or load in many different formats. Now, one key point is that MLatom supports really a wide variety of models, and they range from, as mentioned before, from quantum mechanical to machine learning and their combinations. And in terms of quantum mechanical methods, we support ab initio approaches, DFT, semi-empirical, and for machine learning, you can use pretrained model, like you just used one, or you can create your own models, so you train them yourself, and again, we have tutorials for this, and then you can use them also as the same way to do geometry optimization or dynamics. And all of these models benefit from interfaces to many different packages, state-of-the-art packages, like the Ani, which we used, is a result of interface to Torch Ani package, but many other methods are also provided from different packages, as you can see in the overview here. Of course, we have also our native implementations for methods, and For example, hybrid QML methods, they are implementation based on interfaces, but we have some unique way to represent them and implement. And there are some recommendations how to use them, what are the strengths and weaknesses of them. Also, it describes different machine learning approaches, some more advanced methods like designing from scratch your models, like kernel methods. And you can also design some more elaborate composite models, here shown on an example of AIKM1 approach, to which we come back later. So this approach consists of many different components, like semi-empirical methods. On top of that, there is neural network corrections, default corrections, dispersion corrections, and neural network corrections also consist of many neural networks. So you can design this yourself, and then we provide tutorials, like for example for single points calculations. You can click and check how to run simulations, like here for some isomerization reactions with, again, example how you can use Bistrelief approach through the interface to Gaussian, or you can also use it with AIKM1, which is approaching couple cluster accuracy, so even better than Bistrelief, but will be even faster. And here is an example how simple it is to use. And the nice thing about the MLatom that usually it's again data driven, so you can put in this XYZ file many coordinates, many molecules, and then it will calculate them all together and print properties for all of these molecules. And this is for comparison. It takes much less time to do the single point calculation with the AIKM1. You can try it again on the cloud. And while with Bistrelief it takes longer, and also its agreement with references worse. So if you go back to the overview, there are some bigger examples from real molecules, which are more interesting for experimentalists, for example. And these are big molecules, and here it shows that even for such big molecules, it takes minutes, while with DFT it will take you many CPU hours. Going down to the overview, we support also many, of course, relative energy calculations and different thermochemical properties, like Gibbs free energies and enthalpies. And especially in Python API, it's very easy to construct workflows where you calculate relative energies in one script, and then you can compare directly with available reference data. Again, here is example how AIKM1 performs well, and that's why it's a recommended method if you can use it. The script is here provided for you, which is easy to copy and paste and run yourself the calculations. Now it also has very accurate Hitza formation, and MLatom has a very good and convenient implementation of it, that you can directly obtain Hitza formation printed at the end of calculations in the output file. And if it can calculate it, and then you can compare again to different methods. You can do it in Python API or by simply provided frequency keywords in the input file. And it's pretty straightforward, as you can see. Then you will also get vibrational analysis for molecules with frequencies. And as mentioned, Hitza formation here is printed, kcal per mole and heart rate, 298 Kelvin. More than this, you can also run molecular dynamics with many different approaches, from quantum mechanical to machine learning, like AIKM1 or ANI1CCX, again here shown. And also in two modes, either Python API via our native implementation, and also command line input file. So input is pretty straightforward. You would need some initial conditions, and it means initial geometries and velocities. Once you get them, you can run, for example, using NVT ensemble with no fluid thermostat at some defined temperature with your time step, and this is time in femtoseconds. And then you can dump the trajectory, for example, use H5MD file or XYZ file, and then see some results. As these are quite big molecules. You can also use MD with machine learning models trained by yourself, and here we provide some example. You can download this model pre-trained for you, but you can also find tutorials how to train the model. And then when you run this simulations, you will get trajectory in different formats, also like energies, total energies, potential energies, kinetic energies, and so on. There are some unique properties like quantum dissipative dynamics, and also you can obtain spectra from, I just shown you before, frequencies from harmonic oscillator approximation, but you can also obtain infrared spectra from molecular dynamics, run, for example, with the IQM1. And once you do this, it's shown in the paper, you can post-process your trajectory, and so once you run the dynamics, you can post-process it and obtain infrared spectrum plotted for you conveniently with simple input file or with Python API. It's up to you. And other types of spectra, we have unique implementation of one-photon UV absorption spectra with machine learning acceleration through the interface to a Newton X program by Mario Barbati, and then you can see how easy it is to do, so you can automatically obtain the spectrum, publication quality spectrum. We have unique implementation of two-photon absorption done in collaboration with Professor Chen Wang, and you see that also input is pretty straightforward. You provide a smile stream of your molecule, some other data for range of the wavelengths you want to simulate, and data for the solvent you want to choose, and then you get two-photon absorption spectrum. And of course, since it's machine learning package, there are many ways to train the models and validate them and do hyperparameter optimization and testing. So here for training, we have many predefined types of machine learning models, and if you use one of the popular types like crack model, which is quite fast to train a small data and quite robust, you will get result pretty fast and quite good accuracy for small data set like here. Well, you can also play here with any neural network or other neural networks and obtain also check yourself how it performs. So there are some tutorials, for example, for the more recent implementation of the Maze equivariant neural network, and you can check yourself. Here is also a view of different types of neural networks, and we provide also here different ways how you can create the model, how you can run it using, for example, the xCloud computing, or even using Google Colab. And after this, it also shows how to use a trained model to do, for example, geometry optimizations. And with this, you can also train custom machine learning models like data models. We also have some examples, like if you go, for example, to geometry optimizations tutorial at the very bottom, there is example of more advanced model when you design your own delta machine learning models and run geometry optimizations. So going back here, I also want to thank first of all to all the contributors to the package, and we have many of them. So as you see, there are many authors in the paper, so they all did a great job in contributing many unique features and also via discussion and advice. We have a contributor section down there in the paper. They can get more information about this. Also, you can check how to contribute yourself. We highly strongly welcome your contributions. So if you want to contribute, you can make a fork and then develop yourself modified program as you wish, and then we would be thankful if you make a pull request or basically ask us to incorporate your implementations to the main repository. And if you have other questions, we have here channels, different channels like email and Slack, and they were shown here. You can scan the QR code, also follow the links which are shown in the description to the video. And if you have any suggestions what you would like to overview in the next videos, please also leave in the comments.